Okay, we will work on this example. A refrigerator uses refrigerant 134A as the working fluid and operates on an ideal vapor compression refrigeration cycle between 0.14 and zero point 0.8 megapascal. If the mass flow rate of the refrigerant is 0.05 kilograms per second, determine part A, the rate of heat removal from the refrigerated space and the power input to the compression. Part B, the rate of heat rejection to the environment. And part C, the COP, that means the coefficient of performance of the refrigerator. So, so let's we assume things, right? So normally we assume these assumptions. So the assumption one is, except for the expansion through the valve, which is a throttling process. If you remember, we have four components: compressor, evaporator, expansion valve, and the condenser, right? So the expansion valve, we assume that the process undergoes in the expansion valve is a throttling process, right? Therefore, there's no heat transfer and also there are no work involved, right? And the whole process of the refrigerant are internally reversible, right? So all the processes are reversible process. The compressor and the expansion valve operate adiabatically, that means isentropically, right? Adiabatic means, again, no heat transfer, only work are involved, right? Kinetic and potential energy effect are negligible, and saturated vapor enters at the compressor. Now this is important. Now what is enters the compressor is the saturated vapor, 100% 100% gas, right? Vapor, and the saturated liquid leaves the condenser, right? So what leaves in the condenser is saturated liquid, right? So with that we will work on the example. Now this is the diagram, right? So okay, now this is a TS, right? This should be TS diagram, right? Temperature and entropy diagram, right? So right, so this will be temperature, right? This will be entropy, right? So so this is our thermodynamic cycle. Now let me start from here. Now what is exit from the now this is Q in, what is exit from the evaporator. So this evaporator is a 100% saturated gas, right? That means enters for the compressor. Now that is what is our assumption is entry point for the compressor is 100% saturated gas and compressed liquid, and compress the gas such a way it increase the pressure. Now this is our high pressure line. This is a high pressure line, goes like this, right? And the low pressure line, right? So low pressure is 0.14 bar, high pressure is 0.8 megapascal. Okay. Then so this is the compression process, compress it. Then we have heat rejection process to the environment, that is happening in the condenser. So what the condenser do is remove the heat to the environment such a way it cools from superheated all the way to 100% saturated gas, then 100% saturated liquid. Then we have throttling process in the expansion valve, right? Normally entropy increases. We consider when we are throttling in a valve, entropy expand, right? That makes entropy what we call increases, right? Then 4 to 1 we have evaporative process in the evaporator, where you have mixture of liquid plus gas, and the heat absorbed by the gas, right? So such a way we feel the coolness, and once they absorb the heat and it become a 100% saturated gas, right? So this 100% gas here, we have mixture here, and we have 100% gas here, right? So that is the process. So compressor here and the condenser, throttling valve or the expansion valve, and the condenser, sorry, evaporator. Okay. So these are the values given in the example in the problem, and mass flow rate is given as 0.05 kilogram per second. So the part A is rate of heat removal. So if we rate of heat removal, that means 4 to 1. This is where the heat is removed from the refrigerator space. That means this is the evaporator, right? So evaporator is here. So that means if you are considering a AC system, the evaporator should be in your room. So the air will be circulated through the evaporator. That means in here. So the heat is absorbed by the evaporator, right? That means the working fluid. So effectively, a participant will feel the coolness. Okay. So heat is removed. So the people inside the room will feel the coolness. Okay. So that is what is happened here. So the heat rate of heat removal is then therefore H1 minus H4, right? Then power input is where this is where the power input is, right? So we have compressor, we supply electricity for this one, therefore electricity convert into the mechanical power, therefore work in is here. So the power input is therefore H2 minus H1. So these are the two quantities that we need to calculate. So if we can find H1, H2 and H4, therefore we can answer answer A and B, right? So so we know the pressure, right? Therefore we know this point exactly. Now this is in the saturated line, right? We have 100% gas line, therefore we can refer saturated tables, right? Saturated table under pressure 0.14 bar, right, to figure out this value here, right? Therefore from R134 saturated table we can find H1 values, right? So let me go inspect property table. Now we are interested in saturated refrigerant 134A. We have temperature table and we have pressure table. Since we know the pressure, we can follow the pressure table, and also we have to follow the superheated table as well. R134 is superheated, R134 is saturated pressure table, right? So A12 and A13 we go, right? So this A12, so our pressure line is right 14 megapascal, that means 140 kilopascal, right? Right, so we are looking in 140 value right here, and if you look on this line, right, this is the line we are interested in. So you can see Hg value 239.16, right? So Hg value 239.16. So that is the value in here, right? 239.16, right? And the same time we can extract the S value as well, entropy value as well, 0.94456, right? We go back and see 0.94456, this is the value, right? Because we are in the gas, right? 100% gas, therefore we are referring to the gas value, right? The same way in here gas value, and the entropy also the gas value, right? Okay, because we are in this 0.1 here, right? We know 100% it is 100% gas, right? Okay. Then so, and also we know this is isentropic compression, right? Adiabatic compression, therefore S1 should be equal to S2 as well, right? So we can write S1 equals this amount, also equal to S2 as well. Then since we know this 2, right, we can again refer 134 superheated table to figure out the point at point number 2, right? So we know this S2 value, and we can refer superheated table because this is superheated region, superheated table to figure out the number 2. So S2 is known 0.944, right? Therefore if we refer the superheated table, so our pressure is 0.8, that's mean 800 800 kilopascal and 0.8, so 0.8 megapascal. This is the pressure we are interested in, and our value is if you remember 0.944, right? It should between these two, saturated and the saturated temperature, and between this one, right? Value between these two. Okay, therefore if we extract these values, right? So lower value is 9183, right? 9183. The upper value is 9480. Our value is in between 0.944, right? So the same way we can find the portion. So portion become this value 0.884, and also we can extract the H values as well from the same table, right? So if you look on the H values, so this is the upper limit, this is the lower limit, right? Okay, then since we know the X value, that means the portion, then we can calculate the H2 value. So H2 value become 275.38, right? So we know the H2, we know the H1, H2. The next thing is H3, right? And if we look on the H3 values, we know the exact point, right? So H3 is in here, right? This is the H3, and it is in 100% liquid under 0.8 megapascal, saturated line, saturated 100% liquid. So therefore we can refer saturated table, right? For R3 for a saturated table, if you look at saturated table, right? So this pressure is 800, and our value is fluid, right? The liquid, therefore 95 point is the value, 95.47 H value, right? 800 H value, HF 95.47. so that is what is getting here, right? In here, okay. And same way we can find the S value as well, right? Since we are throttling, the next process is throttling, so we know H1, H2 and H3, right? And since we are throttling under the assumption that's in the expansion valve, so the throttling process, there's no heat transfer, the same way there's no work involved, therefore we can simply determine H3 equals to H4, right? Now therefore we know all the things, H1, H2, H3 and H4, right? So therefore we can simply substitute for the equation. So the heat removal is equal to m dot into H1 minus H4. So when m dot is given in the as a data in the question, therefore we can substitute this value and we get a 7.1845. Same way we can do the power input equal to m dot into H2 minus H1, so it become 1.88811 kilowatt. So that is there. Part A is okay, right? Heat removal from the space is 7.1845. Power input is 1.811 kilojoule per second, that means kilowatt, right? Then the part B is heat rejection to the environment. So what is the heat rejection? So this is the heat absorption from the refrigerator space. 4:1 is heat absorption. The heat rejection to the environment is Q out 2 to 3, right? 2 to 3 it is happening in the condenser, right? 2 to 3 heat rejection for the environment. Therefore H2 minus H3 into M1 is the heat rejection. So that is what is shown here, heat rejection m dot into H2 minus H1, and become like 8.99. Okay. Then the COP, coefficient of performance. So coefficient of performance for refrigeration is the cooling effect divided by the work input. Therefore the cooling effect is the one that we have calculated in the above, 7.1845 divided by the work in 1.811. So that's become 3.967 roughly equals to 4. Now, what is this COP means, right? Now, what is actually mean is, if you give 1 unit of work in, let's say 1 unit of energy, that means if you spend 1 unit of energy, you can get 4 unit of cooling effect. That's what this means, right? That means if you put 1 unit of electrical energy, right, 1 unit of electrical energy, 4 unit of cooling effect will be achieved, right? And again, this is for COP for refrigeration. The same way we can define the COP for heating effect, that means heat pumps. So it is always COP of heat pump, right? That means heat pumps equal to COP refrigeration plus 1, right? So this is true, right? Now if we use this refrigeration cycle as the heat pump, you will get COP of heat pump equal to 5, right? That is true, right? Because whatever the energy input in here will be dissipated in here. That means the 4 unit of energy, 4 unit of heat energy will be absorbed in the evaporator, and 1 unit of electrical energy will be transferred to the fluid in here, and all the 5 unit of thing. So 4 into 1, 5 unit of heat energy will be dissipated to the environment, right? That's why COP become 1 plus COP of refrigeration, right? And again, let me discuss about the why heat pumps are using. Now heat pumps are normally used for heating purpose. In the the colder countries, they are using heat pumps. Now alternatively, you can use electrical heating. Now the space heating we are using heat pumps, and also there are another alternative, electrical heating. Now if we compare both things, electrical heating plus heat pumps heating, now the COP of heat pump is much higher than the electrical one. Now if you use the electrical heating, let's say your input is 1 unit of electrical energy, you will get roughly 1 unit of heating effect output as the output, right? Because 100%, let's assume if that apparatus convert 100% electrical into heating, then 1 unit of electrical energy will be converted into 1 unit of heating energy, right? But if you use a heat pump in this case, right, if you put 1 unit of electrical energy, you get 5 unit of heating output. That's why most of the countries using heat pumps as for its heating, space heating scenarios, right? And also there are drawbacks also, because now this is economical, but in the other sense, initial cost for heat pump is much higher compared to the electrical heating. Now electrical heating is much more complex. What you need is simply a resistive wire, so it will heat up, right? But it's not as that in the heating pump. You have compressors, you have evaporators, right, valves, and a lot of things are there. It's a bit more complex, so the initial cost is higher compared to electrical heating. And also there are some very cold situation, like very colder situation, things will clog up. Now you have working fluid there, it will freeze out in the tubings, and everything will freeze out such a way that it is not always the best solution to use the heat pump to space heating situation. But most of the scenarios you are using heat pumps, and so normally they are using both in the electrical heating plus heat pumps to heat up the environment, right? So that's it, and with that your session is over, and your scope is achieved, right? So so I'm going to stop on this session, and let me meet you in the exam. So again, exam, a little bit of exam. Exam will be open book exam, and you have to bring the what we call table, property table. Get a print of the property table, and you have to bring that one in the exam, right, to the exam. Okay? Because we are not providing any property table, because it will be a cost to provide lot of property tables. So therefore you have to print your own one and bring that one to the exam, and the exam will be open book one, right? Okay, right.